So once again, sorry, I didn't have a mic. So great to be here. First time in Ukraine, I have to say. First time in Kiev. It's a really exciting city. We walked around yesterday, and really interesting conference. So my name is Christian. I work as a software engineer at Canonical. I'm a kernel engineer there and also maintain the Lexi and LexD projects. And so it's basically a container runtime. And today I want to talk about file system mounts in user namespaces, which is work that has been going on in the Linux kernel for quite a while, like for a couple of years. And I basically just showed up for the fun part of like reviewing the last bits that are required to make this work. All of the heavy lifting has been done by other people, but I will mention them during the talk. So exactly. Let's start with namespaces. So how many people are familiar with namespaces? Wow, that's quite a few. How many people are familiar with user namespaces and how they work? That's a lot less. Probably something to do that not a lot of container runtimes use them at this point in time. So right. What are namespaces? Namespaces are basically a way to virtualize certain aspects of a system. And you all might have heard at this point about namespaces simply because they are an essential building blocks of containers and container runtimes. The way I put it is there is not a single global namespace in contrast to traditional virtualization methods, but there are a couple of them at this point. So we have mount namespaces, PID namespaces, UTS namespaces, IPC namespaces, cgroup namespaces, network namespaces, and finally, the one I need to talk about to make this all work, or for you to be able to understand what I want to get at, is the user namespace. And it's pretty mundane. I'm not going to be talking about all of those namespaces, but I'm just mentioning a couple of them to illustrate what they're actually doing. So the first one, and also one of the most interesting ones, is probably the mount namespace. So what does a mount namespace allow you to do? Let's say you create a new mount namespace, unshare m, you're placed in your mount namespace. Let's ignore mount propagation for now, and let's say, because it's pretty complicated and it messes things up. But the idea is when you unshare a new mount namespace, you get per process mount name tables. Which means if you do it right, if it's not set up MS shared, which is a mount propagation property, you will be able to do mounts and umounts in the new mount namespace that you created without affecting any of the mounts in your parent mount namespace, which is pretty cool. So you, for example, could plug in a USB stick and you want to make sure that the user that mounts that USB stick will not pollute the host mount namespace, so you don't want this mount to show up in the host mount namespace. You create a new mount namespace, you mount that USB device, and you won't see it in the parent mount namespace, you only see it in the child mount namespace. I also, for the sake of precision, I should mention that mount namespaces are not really hierarchical. So that means basically you cannot, for example, see all of the mounts in all child namespaces from the parent namespace because they're pretty isolated. The second one, and this one is a hierarchical namespace, is a PID namespace. And it's the same concept. You create a new PID namespace. And basically, you start, the easiest way to understand this is you start numbering your processes in the new PID namespace anew. So you have PID 1 inside of a new PID namespace, but on the host, it will appear as a totally different PID. That's the whole idea. And they are hierarchical in the sense that from the parent PID namespace, you can see all of the processes of all child PID namespaces. User namespaces, by the way, are also hierarchical for pretty obvious reasons, which we will see later. There are a couple of other namespaces in the works. There was an idea about a time namespace. This is a patch set that the Creo guys, the Virtuoso guys, maintain and actually have, and I think they're about to push it out soon. We're going to give a talk at another conference later this year, Linux Plumbers, about this, which would basically mean you add a new flag to the clone system call, and then you create a new time namespace. If it ever gets merged, is another discussion to have. Device namespaces is something that we once thought about. It's probably not going to make it in its traditional form. We've namespaced U-events, which basically are a way to, the kernel gives you messages about what devices you plug in, and we have tied those U-events to namespaces, and basically we have a user space-based device namespace, but it's probably not going to be a separate flag for the clone system call. And there once was an idea about IMA namespaces, but that's probably also not going to happen. So we're stuck with 6 right now. Maybe we'll have more. So, there is one big problem. So what I said is what kind of namespaces you use in your container runtime or in general for your isolation sandboxing solution, favorite sandboxing solution, for example, systemd services and so on. You determine how isolated your app is going to be from the rest of the system, right? That's the whole idea. So it's pretty important. But one of the problems is that none of these namespaces that I've mentioned before, apart from the user namespace, obviously, will isolate privileges on a standard Linux system. That means just because you created a new mount namespace or a new network namespace, you will still be able to shut down the host, you will still be able to join files, and so on. You have all the privileges that the initial host namespace actually has. And that's going to be a problem if you want to run untrusted workloads, which obviously a lot of cloud providers do, and also in your systemd service, you want your users sometimes to be able to run certain programs that you don't necessarily trust. So it would be cool if you had a concept or a way of isolating privileges on a standard Linux system. And this is where the user namespaces basically come into play. They do just that. It's a namespace that is concerned with isolating privileges on a standard Linux system, or Nixoid system for that matter. The requirements, they seem pretty obvious when you think about them. Coming up with them is probably a lot harder, I assume. But the idea is basically the first step, you want to separate the host IDs from the user NS IDs. Why? Because the IDs, UIDs and GIDs, they're the primary bearers of or carriers of privileges on a Linux system, right? They determine if you're UID 0, you can do everything. If you're not UID 0, you can do a lot less things. So you want to separate the privilege that the host IDs carry from the privilege that the user NS IDs carry, so that you can guarantee that if you perform an operation inside of a user namespace, it does not necessarily affect the host or can affect the host. That's pretty important. You also want to have a user NS root ID. Why? And what do I mean by user NS root ID? I mean you want to have a UID 0 inside of a new user namespace, the same way you have a UID 0 on the host. Why? Because you want to have the same syntax and semantics for UIDs and GIDs inside of a new user namespace than you have on the host. So you can have structurally identical permission models. Basically, that's the idea. So you have a privileged UID over the user namespace, meaning UID 0 inside of your user namespace can do all the things that UID 0 can do on the host, just with restricted or more restricted privileges, essentially. We can try and see if the presentation works. And if you can even read it. Wait, before you click on it, please, one second. So the thing is that sometimes you don't want to have a root ID inside of your container, right? Sometimes you, for example, you say, this app is so untrusted or whatever, I don't want the UID 0 even inside of a user namespace. Even if that UID 0 inside of the user namespace has no privilege over the host initial namespaces, I still don't want there to be the UID 0 inside of the namespace. So you can, for example, only map your own UID. That's a possibility. You can click on it. Cheers. Wow, that works. So what I do is I'm sharing new user namespaces. I'm just using standard tools now to illustrate how this works. You look at UID map and GID map, and you see that there is no mapping defined. So you're a totally unprivileged user right now. And now you can use standard Linux tools, in this case, UID map and UGID map. You give it a PID, you give it a user ID inside of the namespace on the host, and then the range, and then you can look at procself UID map and procself GID map. And you see that you have written a mapping. But you haven't mapped root UID 0. You only have mapped your own UID to your own UID. So you have no privileged UID. You can switch back to the slides. Thank you so much. So you have no UID 0 inside of that namespace. So you are much more isolated than if you had mapped one. You also want to make sure that nesting is possible so that you have layers of user namespaces. So you can create user namespaces inside user namespaces and so on. You can create as many as you want. Oh, well, actually, it's not true. The kernel has a limit of up to 32 user namespaces by default, I think. You also want to make sure that your user is root ID, so UID 0 inside of your new user namespace or container that uses user namespaces is not privileged over any resources it does not own. So you shouldn't be able to mess with any global properties like, I don't know, let's assume for a second that the open file limit would be global for the whole system. You should not be able to change it even if your UID 0 inside of a user namespace, unless it's per user namespace. Also, you want to be able that unprivileged users should be able to safely create a user namespace. That would be pretty nice. So that they can basically create a new environment in which there are UID 0. Okay. So how do you do this? And this is from a more technical perspective, basically, you set up a bijective mapping between host IDs and user NS IDs. The way this works, what I mean by this is you basically choose two sets of equal size of user IDs, so a set of user namespace IDs and a set of host IDs, and then you establish a mapping such that you map each user NS ID onto exactly one host UID. That's the idea. But you don't, that's what I said before, you don't need to map all of the UIDs or GIDs that you select. You can choose arbitrary subsets. So for example, let's say normally on a standard NIC system, you would say, I want to map user ID 0 to 65536 inside of my new user namespace to a set of completely unprivileged host UIDs and GIDs. So it's, for example, say, I map UID 0 inside of my container to UID 100,000 on the host, and UID, and then for all UIDs up to 65536, which is a full POSIX set of UIDs and GIDs. So UID 0 to 100,000, 1 to 100,001, and so on. And if I do this, then I have like the same permission model exactly inside of my user namespace than what I have on the host. So that's what we would call an isomorphism, because you have structurally identical permissions models. You have a UID 0 that is privileged over your user namespace, just as you have on the host. But you could also decide to just take a subset, for example, just map your own user ID. So you take user ID 1000 and user ID 1001 and map it to user ID 100,000 and 100,001 on the host and no other UIDs and GIDs. This becomes important for file system mounts later on, that you can actually do this. Okay, can you click on this link? I'm so happy that I recorded all my demos. So what I'm doing right now is basically I'm doing just that. I'm establishing a mapping. And what I do, I specify 4 individual mappings. I'm saying 1,000 on, you can click play. Thanks. Lexi userness is a binary that lets you run arbitrary commands in a user namespace. That's the idea. I map both UIDs and GIDs, and I say I'm mapping UID 1000, UID 1001, UID 1002, and UID 1003. And if you want, you can skip a little bit further because I'm obviously very bad at typing. Why did I do so many? Why did nobody stop me when I did this? Tycho, you were sitting next to me. So, and now if we look at proc, self, UID map, and GID map that record the mappings, you can see I have 4 individual mappings established. That's the whole idea of this bijective mapping, essentially. But I can specify the same thing because we allow you to specify ranges. I can see I want to map 4 UIDs and GIDs at the same time, and then you can see it's the same type of mapping. It's just that we've specified a range. The first one illustrates how actually this sort of bijective mapping works. Thanks. You can go back to the slides. Right, so, Okay, now we have a user namespace. This isolates all of your privileges, and now we need to make sure that all of the other, basically all of the other privileges, apart from UIDs and GIDs that come on a standard Linux system, are also isolated. And the way we basically do this is by introducing a concept of an owning user namespace. The first candidate that we have, obviously, are capabilities. Capabilities were introduced as a way to split the root privilege on a Linux system into distinct sets of capabilities, such that, yeah, you don't have a single root that can do everything, basically. What you want to make sure now is that if you create a new user namespace, you start off with a full capability set, just like you would as UID 0 on the host, but all of those capabilities now belong to the user namespace you created, not to the host user namespace. So the kernel can then go on and make permission checks such as, does this UID have this capability in this current user namespace? And if it has, it is allowed to perform that operation. Now, that is only partially true. There is a very annoying snag here, namely that for some capabilities, because they basically regulate whether you can operate on a global resource or not, for example, on hardware, they will always be checked against the initial user namespace. So the kernel will always look at the initial user namespace and see, are you privileged in the initial user namespace? Do you have this capability in the initial user namespace? Even though you have that capability in your current namespace, the kernel will still deny it. A pretty famous example for a long time has been the make-not syscall. So if you called make-not to make a device node inside of a user namespace, the kernel internally would look, do you have the capability in the host user namespace? And you obviously don't have this capability in the host namespace, so you're not allowed to do this operation. That has sort of confused people a lot, because they were like, I have this capability inside of the user namespace, but I cannot perform this operation. That's pretty annoying. We've changed this recently, so now you can actually make not inside of a user namespace, so you can create device nodes, but for various reasons, which we'll see in a bit, you cannot actually use them. Owning user namespace. This concept also applies to all other namespaces, meaning if you unshare a new user namespace and then you create a mount namespace or a network namespace or any kind of other namespace, it will basically get a tag in the kernel saying, oh, your owning user namespace is the user namespace in which you just have been created in. So what this means, if you create a new network namespace on the host, then the kernel will record, okay, you created a new network namespace, but your owning user namespace is the initial user namespace. If you now unshare, so create a new user namespace, the kernel will still keep the same tag on the network namespace. You still will be owned by the initial user namespace, not by the user namespace you just created. So you will not be able to affect that network namespace, even though you have created a new user namespace and are UID 0 inside of that user namespace. That gives you a lot of flexibility. So the way usually container runtimes do it, or you could do it, is you unshare a new user namespace, you create a bunch of other namespaces, mount namespaces, and so on. They will all have the user namespace you created first as owning user namespace, and all checks by the kernel will be charged against that user namespace. And the last one is, and I think this is something I mentioned before, are basically resources. So any resources that are global or that you do not own or do not belong to your user namespace, you should not be able to affect. So you also need to verify that the checks you perform for global resources always are checked against the initial user namespace. Okay, so cool. Now we have all that. We have a concept of a user namespace that isolates sort of privileges, and is super useful. Like you have untrusted workloads, you probably want to use a user namespace just for security reasons, just for security reasons. But they obviously come with a lot of restrictions. I mentioned a bunch of them right now, and things you need to keep in mind. And it's an endless source of bugs, obviously. So one of the things they also restrict user namespaces for a long time, or have restricted, is mounting. So apart from a few file systems like, which are basically in kernel file system, tempfs, sys, and proc, and even they come with some restrictions, you are not able to mount anything inside of a user namespace. And there are a couple of reasons for that, and I'm not going to go into all of them, but I'm going to mention a few. So the first one is obviously device files. So imagine you would be able to mount a new file system inside of a user namespace. I mean, this is a general attack, but it's more clear on file systems. You mount it. If you can mount it, you are the owner of the file system, essentially, and now you can do anything you want with it. For example, you can create device nodes. And what's the problem with being able to create and use device nodes? I know a guy who writes into random kernel memory. So you could basically create defmem or defkmem and then open it and write random bits into kernel memory. Or you can do, basically you can get access to anything you want, to your root file system, whatever. So it's pretty important that this is not possible. SUID bits, so the setuid and the setgid bits, obviously, and file system capabilities are also off the table. Why? Well, think about it. You can establish a mapping to UID 0 for your own user ID, always. That's trivially true. You can create a new user namespace as an unprivileged user. Now, you map your own UID to UID 0 inside of your user namespace. You set a file system capability, whatever you want. Let's assume that would be possible. Then you switch back to the host, and now you execute the files with privileges. That's the standard classic file system capability attack surface. So setting file system capabilities for a long time has not been possible inside of user namespaces. And the last one are unmapped IDs. And this one relates back to that's why I introduced this idea of subsets of user IDs that are mappable. So for example, assume you just map your own UID, and you're placed in a new user namespace, and all of the basically files that belong to another UID that you have not mapped inside of the user namespace will belong to nobody, no group. So, but now, if you access one of those files, let's say you do a touch or a LSAL on such a file, you update the access time of those files, right? So the kernel will trigger a write back on that inode. But because there is no mapping, you're corrupting the inode. So you cannot, from the kernel's perspective, you must make all of the files that do not have a mapping inside of user namespace read-only. Otherwise, you're pretty fucked. Okay, so so what do? Enabling file system mounts in user namespaces. How do we go about this? So one option, or the first step essentially that you need to take, you need to be changing the VFS infrastructure. So who knows what the VFS is? Okay, a couple, but it's pretty simple. It's a virtual file system inside of the Linux kernel that defines when something is allowed to call itself a file system. It's basically an abstraction that provides uniform access to all kinds of file systems. So if you want to get a file system inside of the Linux kernel, you need to fulfill the requirements of the VFS, essentially. So that's it. And the VFS records mounts, for example. There is called something like a VFS mount, and it will track who has mounted the file system. And for a long time, obviously, if you mounted a file system, only one guy could mount file systems. That was root. So you recorded the initial user namespace on that file system, or it wasn't even required to record the user namespace. So what had to be done is you needed to introduce a new member in the structure, the superblock structure inside of the kernel, where the superblock structure is a structure that records a bunch of information about file systems in the kernel. What type of file system and so on. What kind of flags was it mounted with and so on. So you add a new member called suserns, which is a pointer to the owning user namespace of the file system, meaning if you mount that file system, the kernel will record the user namespace of the caller that mounted that file system. So now you have the concept of an owning user namespace. You now always know or can track inside of the kernel who actually mounted that file system. Second, and this relates back to something I said before, you want to be able to restrict access to device nodes. So even if you are able to create device nodes on file systems you mounted, you want to make sure that they are not usable, essentially for the same reason I said before. You don't want someone to do defkmem and then write into random kernel memory. The way you do this is you could say, okay, let's mount the file system always implicitly with ms-nodef. That won't work because you can always remount the file system and strip the ms-nodev flag. So what the kernel does internally, it introduced a new flag called sbi-nodev, which is an internal kernel flag that basically tells it, on this file system, no matter how many device nodes you create, you will not be able to open them. You will not be able to use them in any meaningful way. And third, and this relates back to the file system capability stuff I talked about before, you need to namespace file system capabilities. You definitely want file system capabilities because they're pretty useful. They allow you to do stuff like execute ping as an unprivileged user, and you want to be able to unpack, for example, a tarball in a new user namespace and retain all of the capabilities that that the files came with. This is possible with a new patch set. How am I on time, by the way?
Actually, not much.
Okay, so we skipped the demo. I can hurry up. Well, let's say we have all figured this out. So the VFS is ready to now safely delegate file system mounts to you. Do you say, okay, it's fine, the infrastructure is there, it's good to go? Well, there is one problem left, obviously. The VFS file system robustness is different from file system robustness in itself, meaning there is nothing in the VFS that prevents a malicious user in its root from mounting a corrupted file system image, right? That's a guarantee that each file system individually needs to give you. So if someone, let's say, created a new user namespace, UID0, somebody sends me a file system image, it creates it's basically corrupted. As soon as I mount it, it crashes my kernel. That's the idea. If an unprivileged user is now able to mount it, you have a large attack surface. And the VFS has no way to guarantee that this is actually safe to do. So each individual file system inside of the kernel, basically each maintainer needs to come to you and say, it is safe for an unprivileged user inside of a new user namespace to mount a file system image. And it turns out not a lot of kernel maintainers are willing to make that guarantee. Basically no one. So if you thought we sort of flicked the switch and now all of the file systems that you really care about, X4, overlayfs, Oman, CFS, ButterFS, I can all mount them in user namespaces. Nah, it's not going to be that way. Not for a long time, unless someone comes up with a file system that's basically specifically designed for mounting in unprivileged users. Actually, it turns out there is already one, which is Fuse. Starting with kernel 4.18, you are able to mount Fuse file systems as an unprivileged user in a new user namespace. Why is that? Trivial? Well, not trivial, but it's file system in user space, which means it's a kernel module and a libfuse library that you can use to write your own file systems in user space. And so all of your file system code runs in user space, which means it will be a lot less performant and so on. But the fact that all of the file system code runs in user space and not in kernel space gives you a strong security boundary, so it's safe to allow access to it. Actually, the fuser mount binary that you can use to mount Fuse file systems has been a setuid binary for a long time, and you could safely use it for a long time. So all of the other mounts, X4, overlayfs, XFS, and ButterFS, you will not be able to mount as an unprivileged user. If you really care about this specific use case, there are a couple of solutions, and I'm just briefly going to mention two of them. There is the new, a new SecComp patch set that you're going to be hearing a talk about today by Tycho Anderson, which is basically, let's say inside of your user namespace, a container or whatever makes a mount call to mount some X4 file system. Then you can basically set up a listener on the host that retrieves the syscall and then can decide for the process inside of the container if that syscall is supposed to be successful or fails, then perform that operation for the process inside of the user namespace and report back success. And so you have mounted a file system. Requires privileges, but it's one solution. And the third one, and the second one is the new mount API, which is currently going into the kernel. And the idea is you split the open mounting and configuration of a file system into separate syscalls. So you have an fsopen syscall that opens a file system tree, gives you an FD back. You have a second syscall called fsconfig, which you set mount options with. And the idea would be the privileged user on the host would mark a specific tree as safe for delegation to user namespaces, like be able to mount this in user namespaces. Then you can send this file descriptor back to, for example, your container, or your container can just call mount on the specific path. Since it's marked as safe for mounting in user namespaces, you will now be able to mount it. This is actually a pretty nice solution. And the last one is LKL Fuse, but I'm not going to mention this. So the people in the background that have actually done all of this work, and I'm just presenting on it, I came to the point where it's basically about hacking and reviewing patches. Was Eric Biederman, who's driven most of this effort. He's a software engineer, kernel engineer at Red Hat. Serge, who is currently at Cisco. Seth Forshi, who's on my team. And Stefan, who's also given on my team, and has also given a bunch of input on this, and so on. So yeah, these people are usually not always put in the foreground because it's not the sexy part of the work, you know. But yeah, these are the people who've done all of the heavy lifting. And that's it for me. I hope I didn't confuse you too much. I know this was a lot of technical details and so on, but thanks for having me.